interpretations and applications of the derivative and the definite integral. What we're going to do today is we're going to start digging into some more application of, specifically of an integral. What can you use them for? If you take the derivative of an amount, you get the rate at which that amount is changing. If I take the derivative of position, what do I get? What's the derivative of position? Velocity. If I take the derivative of your position, I get velocity, which is rate of speed, right? It's the rate at which the position is changing. Don't get mixed up the difference between what a derivative does and what an integral does. For example, if water is being drained from a swimming pool and R of T represents the amount of water measured in cubic feet that is in the pool at any time, measured in hours, then R prime of T would represent the rate at which the amount of water is changing. What units would that be in? Feet? Feet? Cubic feet would be measured in cubic feet per hour. Now, if water is being drained from the pool, what would you expect the derivative to be? Well, no, our unit is going to be cubic feet per hour. But if the water's being drained from the pool, then, I'm sorry? That's right. The derivative, the rate at which the amount is changing is going to be negative because the amount of water is decreasing. Now, we just answered this one. That would be cubic feet per hour. So remember, when you take a derivative of an amount, you get a rate. If you take the integral of a rate, you get the amount of change, okay? If you take the integral of the rate, you get the amount of change. If I integrate velocity, what do I get? Position. So you guys know that if I integrate from A to B, v of t dt, what does the fundamental theorem of calculus tell us? That this would be, yeah, P of B minus P of A, which is just the change in the position. So this is just the amount of change of the position if you integrate velocity. Now let's look at this right here. In the context of the example with the swimming pool, if we integrate from A to B, R prime of t dt, and we get R of B minus R of A, what does that mean? Yeah, well, yeah, between A and B, yeah. So it's going to be the amount of change in the volume of the water, right? The amount of change in the volume of the water. And Ava knows it's going to be less because the water's draining out. So the amount of water that's drained out from time A to time B. The table given below represents the velocity of a particle at given values of t, where t is measured in minutes. Now again, this is velocity. Now remember, Sparks is real big on reviewing all the time. He's in constant review mode. Approximate the value of the integral from 0 to 30 of v of t dt using a midpoint Riemann sum. If we're going to do a midpoint Riemann sum, how many subintervals do you think we should be dividing that interval into? 3. So we're going to do one here, right? We're going to do one here, and we're going to do one here. So the integral from 0 to 30 of v of t dt is approximately, how do I do that? Remember, we're dividing it into rectangles. There you go. So your base is going to be the change in your x value or the change in your t value. So what's the change in my t value or the base of the rectangle in my yellow interval? From 0 to 10? 0 to 10 is 10. 10 to 20 is 10, and 20 to 30 is 10. So I can pull out the 10 because it's common to all three of my subintervals. Times the height of each one of my subintervals. Because where did those numbers come from? The middle. That's right, the middle. Run that on your calculator real quick. What are you getting? 63. 63 what? Cubic feet? Just feet, just cubic feet. What? When you integrate velocity, you get the amount. The amount of the water is measured in, this says feet, doesn't it? Hang on a minute. Oh, yeah. No. I was thinking about the pool. Sorry. I was thinking about the pool. We're working with these numbers here, aren't we? Yeah, it's a different situation. I was back thinking about the pool, and I was going, what? So what does that 63 feet mean? Remember, let's look. The table below represents the velocity of the particle at given values of t, where t is measured in minutes. What does 63 feet mean? Yeah, from in the first 30 minutes, the particles, what? Traveled 63 feet? Or the change in the position is 63 feet in the first 30 minutes? What about this one? What is the value of the integral from from 5 to 25 of a of t dt? And using correct units, explain what this represents. How do we integrate a of t? What theorem did you just use? You betcha. The integral of acceleration is velocity. So it's going to be v of 25 minus v of 5. What are you going to get? 0. 0 what? This is velocity, right? And velocity in this case is measured in feet per minute. What did we find? What does this mean? Not average. We didn't find an average. The change in velocity over or from minute 5 to minute 25. The change in velocity from minute 5 to minute 25 was 0 feet per minute. The change in velocity. The temperature of water in a tub at time t is modeled by a strictly increasing. What does that mean? Strictly increasing. Never decreases, never constant. Always going up. Twice differentiable function, where W of t is measured in degrees Fahrenheit and t is measured in minutes. Okay. What do you think, what does t of 0 equals 55 mean? That's right. When you started measuring, the temperature was 55 degrees Fahrenheit. Using the data in the table, estimate the value of W prime of 12. How are we going to do that? How do we approximate a derivative from a table? No, not going to do a Riemann sum. Slope of the secant line. Slope of the secant line. So we'd say W prime of 12 is approximately, what's the slope of the secant line around W equal 12? What 2 points am I going to use? Yeah, W of 15 minus W of 9 over 15 minus 9. Run that and let's see what we get. Go 3 decimal places. What are the units? Degrees Fahrenheit per minute. Good. What's this mean? We approximated W prime of 12. What's W prime of 12 mean? At 12 minutes, what is? The temperature is increasing, or you could say changing, at a rate of 1.017 degrees Fahrenheit per minute. So at 12 minutes, the temperature of the water is increasing or changing at a rate of 1.017 degrees Fahrenheit per minute. It's great if you can do the calculations, but you got to understand what you're finding. You can be the best engineer in the world, but if you can't communicate what you found, it doesn't do any good. Take a look at this one. Use the data in the table to evaluate the integral from 0 to 20 of W prime of t dt. What's that? Good. According to fundamental theorem, what do you get? Is that right? Hmm? 16 what? What does that mean? From time 0 to time 20, the temperature of the water in the tub changes by 16 degrees Fahrenheit. Yep. You can say increases. You can say either one. So from time 0 to time 20 minutes, the temperature of the water in the tub changes or increases by 16 degrees Fahrenheit. Now, are you going to say per minute? No, because this is not a rate. You're going to get your calculator on this next one. For time 20 to time 25 minutes, the function W that models the water temperature has a first derivative given by that function. Based on this model, what is the temperature of the water at time 25? We're not given time 25. What can we do? Integrate W prime of t from where to where? 20 to 25. How's that going to help us find the temperature of the water at 25 minutes? That's how much it changes, correct? What theorem am I going to be using here? Because if I take the antiderivative of this, what am I going to end up with? Which we have, good. We already know this. That is, what is 71? We don't know this, but we can darn sure find this on our calculator. So take a minute and run that. Let's see what we get. Are you getting 2.043? Okay. So that's W of 25 minus 71. So is it 73.2 point snap 0.043? What? Degrees Fahrenheit? What did we find? We found the temperature of the water at 25 minutes. Yeah. Temperature of the water at 25 minutes. A pan of biscuits is removed from an oven, at which point in time t equals 0. The temperature of the biscuits is 100 degrees Celsius. When you see something like this, I would really encourage you to stop and write something down. Now, if you'll notice here, this is B prime of 3. So I'm assuming that they're meaning temperature is going to be B. So I'm just going to go and write B of 0 is 100. So I don't forget that I have that piece of information. The rate at which the temperature of the biscuits is changing is modeled by that function B prime of t. Now it says to find the value of B prime of 3. How are we going to do B prime of 3? Yeah, just plug it in. Plug and chug. Go. Okay, what did you get for B prime of 3? What is the unit? Degrees Celsius? Is that the right unit? Remember, this is a rate, correct? We measured a rate, and the time is measured in minutes. The temperature is measured in degrees Celsius. So what does this mean? Per minute. What does it mean, that number that we found? 3 minutes after the biscuits came out of the oven? There you go. The temperature is decreasing at a rate of 8.236 degrees Celsius per minute. You can say at time 3, but it's better if you will say in context. 3 minutes after the pan of biscuits was taken out of the oven, the temperature is decreasing at a rate of 8.236 degrees Celsius per minute. No, if you do, that's wrong. You say decreasing at 8 point or changing at a rate of negative. You see the difference? I would count that wrong because that doesn't make sense. No. Now, I want you to graph the derivative. But when you graph the derivative, what I want you to do is set your window the way this graph is set. So your x's, I want you to go from -1 to 11, and your y's, I want you to go negative, whatever that says, -6 to 2. Now, you should have gotten a graph that is completely down in quadrant 4. Now, let's talk about, in the context of this problem, why the graph makes sense. Why? Why is the original function always decreasing? When you take the pan of biscuits out of the oven, what's going to happen to the temperature of the biscuits? The temperature will decrease. That's correct. So that's why. And we'll talk about that in a minute. We know that the rate is always negative, which is why this thing is below the x-axis. Now, why do you think the rate, why do you think it's doing this? It increases faster at first, and then the rate is, it's still decreasing, but slower. Yeah, well, you talk about something I understand. Because I don't understand thermo. Why? When is the temperature going to drop the most? Early after it's come out or an hour after it's come out? Early. Yeah. Right when the thing comes out of the oven, that's when the temperature is going to drop the fastest. That's why the slopes closer to time zero are steeper. Now, the question comes, where is this going to level off? At what temperature do you think? Room temperature, right. Room temperature. So yes, it would level off at room temperature. I would say the graph is in quadrant 4 because time is always positive and the rate is always negative. That's why it's in quadrant 4, correct? Time is always positive, but the rate is always negative because the temperature is always decreasing. The temperature, though, is decreasing more slowly because it makes sense that the longer the pan of biscuits has been out of the oven, the more slowly the temperature is going to be falling. I have no idea. I have no idea. At time 10, at time 10, what is the temperature of the biscuits? Show your work. How do we figure out what the temperature of the biscuits is 10 minutes after the biscuits have come out of the oven? What are we going to integrate? Why 0? Because we know the temperature at time 0. Good. So we're going to integrate that rate from 0 to 10. But using the fundamental theorem, what is this going to give us? Apply the fundamental theorem to this. Look up here. B of 10 minus B of 0. Good. So you're going to integrate. You're going to get your number. But you know this was 100. Yep. So go to a blank screen. You do remember that you can do 0 to 10 of y1, right? Because you graphed it. Don't worry about typing that whole thing in again if you've got it in y1. That's what Sparks tells me. Is that right? So it's B of 10. Yeah. Point 34.183 what? What did we just find? The temperature of the pan of biscuits after it's been out of the oven for 10 minutes. There you go. I don't know what that was, but okay. Do we have 2 more questions? Oh, this is our last page. Okay. A cylindrical can of radius 10 millimeters, guys, let's go, is used to measure rainfall in Stormville. Incredibly unique name. The can has a, that's not what I wanted. I meant to do that. Yeah, for sure. During the first 5 days of the 60-day period, we know that 3 millimeters of rainfall had been collected. The height of the water in the can is modeled by the function S, where S of t is in millimeters. Remember, that's the height of the water in the can. And t is measured in days for 5 to 60 days. The rate at which the height of the water is rising is given by this function S prime of t. Find the value of the integral from 10 to 15 of S prime of t dt. You know S prime of t. Go. Blank screen. What do you get? 11.159 what? When we integrate S prime, what do we get? If we integrate S prime, we get S, right? And S is measured in millimeters. So we got the correct unit. What does that mean in the context of this problem?
Between t equals 10 and t equals 15, the millimeters change by 1.1.
Well, all right. Yeah, from day 10 to day 15, the water in the can did what? Yeah, increased or rose by 11.159 millimeters. Yes, you can say change. At the end of this 60-day period, what is the volume of water that had accumulated in the can? The volume. Wait a minute. Ah, correct. Aha. Because S is just the height. So all we've got here is the height of the water in the can. How are we going to find, how do you find the volume of water in a cylinder? How do you find the volume of a cylinder? Ah, the volume is the area of the base times the height. What is the base of a cylinder? A circle, so the area of a circle is pi r squared. So the volume of this thing is pi r squared times the height. I love somebody who said big base times the height. That's exactly right. I know the radius of this can, 10 millimeters. What I don't know is the height. Yep. So I know I've got pi times 10 squared times whatever this height is. Now, when I integrate, that formula is only for those days. What do I do about the first 5? This S prime of t, t is measured in days for 5 to... Look, during the first, guys, let's go. Let's finish this up. S of t is measured in millimeters and t is measured in days for those days. My question is, what about the first 5 days? It sure it matters. Aha! Look right there. So, Lily said, my height is going to be the 3 from the first 5 days plus the integral from 5 to 60 of b prime of t dt. Now run that and see what you get. Don't forget to add that 3. Was it B? Oh, S. Sorry, I'm on the wrong problem. I'm still on the biscuits. You can see where my head is. Hungry. I'm hungry. What number? Hey, what number did you get for this? Point. Yep. My suggestion would be you must have plugged something in wrong. Something must be typed in wrong. That's your height. That's the height of water in millimeters in that can after the end of 60 days. What do we do with it? Yep, we're going to put that right here. Yeah, but remember we're in cubic what? Millimeters. Yeah. So the volume is going to be, Spark says it's 52,327. But it's in cubic millimeters. You getting that? What does that tell us? What did we just find? Perfect. At the end of the 60-day period, the volume of water in the can is this many cubic millimeters. That's exactly what we found. We got one more. What's the most recent concert any of you have been to?
Juice WRLD. Juice WRLD.
What's that name again?
Juice WRLD.
Juice WRLD.
He died.
Oh, all right. I don't know Juice WRLD, but okay. And I never will. What? The band concert. Okay, then. The rate at which people enter an auditorium for a concert is modeled by the function R. Now you pay attention right there. Do you notice that here it says rate is modeled by R? It's not R of t, it's R prime, it's R. That's the rate in this case. This is the rate at which people enter that auditorium for the concert for 2 hours, from time 0 to time 2 hours. And R of t is measured in people per hour. I'm sorry? What'd you say?
Said it went away.
Oh, VIP tickets were sold to 100 people. They got to like be, like by the stage or on the stage or have backstage passes or something. VIP tickets were sold to 100 people who were already in the auditorium when the doors open at t = 0 for the general admission ticket holders to come in. The doors close and the concert begins at t = 2. If all of the VIP ticket holders stayed for the start of the concert, how many people are in the auditorium when the concert begins?
So,
Where are you confused?
I just don't understand what the concept with the VIP tickets, like how that works.
There are 100 people in the auditorium before they were like the important people or the people who were willing to pay extra because they wanted extra. They were in there already.
Oh, because they already had
Right.
VIP tickets?
The VIP people, the 100 people are already in the auditorium when the doors open for the general admission ticket people to come in.
The amount of people that you have to add to the...
Yes, yes, that's it, that's it. Now, oh, gotcha.
Saying, like, they got in
Oh, gotcha. How are we gonna figure out how many people are in the auditorium when the concert started if I know the rate at which they enter? That's right. If I integrate the rate at which they enter, what do I find? How many people entered? So, what's this gonna be?
It's going to be the thinking plus
The thingy? Be a little more specific on that one. The integral, the integral from 0 to 2 of r of t dt.
plus 1.
There you go, plus 100. Run it, see what you get. And please round to the nearest person. Do not say that an amputee can count as a part of a person.
That's disrespectful.
That is disrespectful. Round to the nearest person. See what you get. What unit are we in?
People.
People. We're in people.
What unit are we in?
What unit are we in? So, how many people? Let me back up. What did we just find?
The amount of people who live there. And at a certain concert.
The number of people who were in the auditorium when the concert began. Use the words in the problem to answer the question.
Yes, ma'am.
Folks, you go to Silver Dollar City, you go to Disney, I guarantee you that the people there, that a select group of people there know at what rate people come into those parks at certain times of the day and certain seasons. That's data that they have. We are finished.
Yes.
Don't forget, good. Don't forget, in this case, like that plus 100, don't forget that starting amount, if there is one. Don't forget it, because that's a real easy thing to do. You're so excited about getting the integral right, you forget the 100. So don't forget that piece.